So the first property that we are going to learn about is the periodic trend of atomic radius. So this we will call it as down left property or DL property. Now let's see the model of an atom. So in the right hand side, you can see this is the basic structure of an atom. So in the central core, we have proton and neutrons. Together we call it nucleus. So in nucleus, we have positively charged proton and neutral neutrons. So these two subatomic particles, they lie in the center. So this nucleus is actually positively charged. And surrounding that, these electrons rotate in their shells or orbits. So these electrons are actually tiny particles or tiny subatomic particles. Those are negatively charged. So in a neutral atom, if we have 5 protons, we will exactly have 5 electrons. For example, if we have, for example, in sodium, we have 11 protons and we have 11 electrons. So in a neutral atom, you have same number of proton and same number of electrons. Now in the first shell, only 2 electrons can be there, and in the next 2 shells, there can be 8, at max 8 electrons. And the way of putting electrons, that first you have to fill the inner circles, only then you can fill the outer circles. So one by one you have to put in the inner circles. So first electron will come here, second electron will also come in the first orbit, next third electron will come to the second orbit, and you have to fill 8, total 8 electrons in the second orbit. Then the next one electron will come in the third orbit. So these things I have discussed in detail in the previous lecture, lecture 5. So you can go and check that lecture. Now here let's take an analogy. So here we have positively charged nucleus and negatively charged electrons are rotating surrounding this nucleus. So these two are oppositely charged. This one is positively charged and electrons are negatively charged. So there is an electrostatic attraction between these nucleus and electrons. So take it as that this core, this positively charged is actually an attractive girl. The more number of protons it has, the girl is more attractive. Okay, and take these electrons as that girl's lovers. You know, one beautiful girl has many lovers. Many boy wants to get that girl's number, right? So similarly, just consider this nucleus is an attractive girl and these electrons all are her lover. Now this girl will obviously attract these boys, all these boys. The boys who are closer, these boys will get more attraction compared to the boys who are far apart, right? So because these boys are feeling some attraction, so they will try to come close. So these orbits, some special cases, these orbits, they get more compressed. For example, see, this will feel some attraction toward this side. Again, this electron, this lover will also feel attraction towards the nucleus, right? Now here all the electrons will have similar type of attraction. Whatever attraction this electron feel, the electrons which are at the same orbital, they will feel the same type of attraction. Now these things you can determine from the effective nuclear charge, which I have shown you to calculate in the previous video, how to calculate the screening constant, shielding effect or screening constant, and how to determine the Z effective. So based upon that, you can understand that how much attraction is there for each of these electrons. Now as these electrons are trying to come close to this attractive girl, so what happened, this orbit, this will shrink, and this will come like this will become a little smaller, and this shrinkage is much more prominent in case of f block elements. D block elements also shrink a little, but in case of F block elements, this shrinkage is more prominent because F electrons are diffuse in nature, so the F electrons cannot do the shielding, and the outermost electrons, they get more attraction towards this nucleus, and those electrons shrink, the shell shrink. Now as this radius shrinks, as this orbit shrinks, the radius, atomic radius also shrinks. Now how to determine the atomic radius? So atomic radius is the distance from the center of the nucleus to the outermost electron. So see, from here we have, this is the center, let's assume this is the center of the nucleus. So originally the atomic radius was from here to here, this distance, right? But as the electrons are feeling some attraction towards the center, so the orbit will shrink, the last orbit is shrinking. So now the actual atomic radius is actually this much. So the atomic radius has also shrinked. So if you increase the number of protons, the electrostatic attraction increases. So the outermost shells may contract, they may shrink, and the atomic radius can also decrease. So this is the way how the atomic radius decreases. Now if you add one more shell, if you add fourth shell, so the fourth shell will come this way, So if you add more and more shell, that time the atomic radius of the atom will increase compared to the atoms which have lesser number of shells. Okay, so these things we are going to observe in the later slides. Let's take a look at this image. So this periodic table shows what is the relative atomic size of the atoms in the periodic table. So you can see the left hand side we have alkali metals. Those are bigger in size, and as we go in the right hand side we can see very small spheres or circles. So these are very small in size. Noble gases and halogens, those are very small in size. So what is the trend? We will see that how it is happening, what are the reasons behind it, why this size is shrinking from left to right. You can see from left to right the size is shrinking, and whenever we are going to discuss a periodic property, we will go from left to right along a period, or we will go from top to bottom along a group. Now you can see from top to bottom the size is increasing, and left to right the size is decreasing. So this is the 3D diagram which shows the atomic radius data of all the elements in a periodic table. Now let's see the trend. We will see it first for a long period. So what are the factors that are working along period? So if we go from left to right, what are the factors there? The principal quantum number is fixed. So along period, the principal quantum number is same for lithium, beryllium, boron, carbon, nitrogen. All are having the outermost electron shell as to be the second shell or second orbit. Okay, so all these atoms have two shells or two orbits. These atoms have three orbits. These atoms have four orbits. So all these atoms in the period, they have same principal quantum number. Next is the effective nuclear charge increases. So let's see this third period. Okay, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. So as we are going from left to right, we can see more and more protons are there in the nucleus. In case of sodium, there are 11 protons. In case of magnesium, there are 12 protons in the nucleus. Whereas in case of aluminum, there are 13. In case of silicon, there are 14. So the last shell is same, but in the nucleus we have more and more protons. So what I said, the nucleus is an attractive girl, right? So if it has more and more proton, so it is more and more beautiful, more attractive. So it will attract the electrons more. So I will try to show it here again. So if this is your nucleus, if you have more and more protons, it will attract more to the outermost electrons. So it will similarly attract all the electrons, even the inner electrons, but the outermost electrons, that will also shrink. So these electrons will come close. These electrons will feel more and more attraction if the proton number increases. So this shell will actually shrink. So the outermost shell will shrink, and the radius, which tells the distance from the center of the nucleus to the outermost shell, so the radius of the atom will decrease. Okay, and another factor is that when we are going from left to right, so the number of proton is increasing. Similarly, the number of electrons are also increasing. So we have more and more electrons in the shells, right? In the last outermost shell. So that actually increases electron-electron repulsion, because electrons are negatively charged, and we know similar charge particle, they repel each other. So that is also a factor, but this factor is not dominant. The other factors are actually dominant. The increase of effective nuclear charge, that is the dominant factor. So as you go from left to right in a period, the effective nuclear charge increases. So although the electron-electron repulsion increases, but that is a minor factor. Because the effective nuclear charge increases, the electrons, the lovers, they feel more attraction to the attractive girl, and the shells come down. That shrinks, because of which we see the atomic radius decreases. So along period, the atomic radius decreases. Got it? Now next see the periodic trend of atomic radius along group. So along group means we are going from top to bottom this way. So what are the factors there? So along group, principal quantum number increases, means the shell number increases. So in the first one, we have this nucleus and only one shell in this one, whereas in this one, we have nucleus, one cell like this, and we have one more shell on top of this. So I'm just doing half circles because I'm not showing the entire circle. Just consider this as an entire circle, okay? Now in case of third period, we have three shells. Similarly, in case of fourth period, we have four shells, then here five shells, six shells. So as we go from top to down, the principal quantum number increases, means the number of shell increases. Now, effective nuclear charge also increases a little bit, but that is a minor factor. So the red ones, I have written the minor factors in the red ones. So these don't contribute much. So even if we see that we have seen a long period that electron-electron repulsion was also a factor, but that was also minor factor. So that's why I wrote it in red. Here also effective nuclear charge increases, but this is a minor factor. So that's why we will ignore it. We will ignore the contribution of this. This I have written just to give you the complete information that what are the factors working. So the black ones are the dominant and these red ones are minor factors. So we can ignore them. But to teach you for learning purpose, you have to learn everything. Now the other factor is the size increases because we have more and more shells, right? But the increasing rate of size for the heavier congeners decreases. Yeah, so the size will continuously increase when we have more and more shell, but the rate of the increase will decrease. Maybe just see here, from 37 it became 152 as in a pm, means picometer. Now after that there is 186, 227. Now if you see from 227 to 248, the increase is very less, and again 248 to 265, the increase there is increase, but the rate of increase is much lesser. So if we subtract this, we can see there is almost 115 picometer change. Now in between lithium and sodium, if we see, that is 34. The change in picometer, I'm just telling you the change in the size. Now sodium to potassium, so that will be here 14, here 27 means 41. Now from potassium to rubidium, you can see the change is only of 21 picometer. Now from rubidium to cesium, the change is just 17 picometer. So you can see as we go in the heavier atoms, the rate of increase, it is increasing, the atomic radius is increasing, but the rate of increase decreases. The rate of change is significantly less in d block elements due to the less shielding of d and f electrons. Yeah, so another factor is when you consider the d block elements, as I told that in the previous lecture, that d electrons and f electrons, they are more diffuse in nature, they have lesser shielding property, so the nucleus attracts the electron much more. Now if you put more and more protons, more and more electrons, still the attraction remains almost same, and because of that the rate of change in the side by side elements, that is small. That I will show you. I'll show you the periodic table. I'll show you here. You see these d block elements. If you see these d block elements, see if you go from top to bottom, the change of the size is less, not very significant. Whereas if you go in the s block elements, you see a huge change, huge increase in the atomic radius. Whereas in case of d block elements, the change is slow. So along the group, the atomic radius increases. Okay, what is the major factor? Major factor is that the principal quantum number is increasing as we have more, as we are going from top to down, the more and more shells are adding. So that's why the atomic radius is increasing. Now this is the chart which tells you Z versus R, means atomic number versus that radius of atom or radius of orbital. Now you can see for the so these are the s block elements. For s block elements, the atomic radius is more for the alkali metals, and as we go along the period from lithium to beryllium, boron, carbon, nitrogen, oxygen, so the atomic radius decreases. So it decreases till neon. So neon, which is the inert gas element that is having lowest one here, and again in the next electron, when we fill the next electron, that goes in the third shell, right? Third orbit. So that's why again the size increases. Here you can see sodium. So again if you put more and more proton and electrons, the size decreases till the next inert gas element, argon. And again if you put one more electron and proton, the size again increases in the potassium. So just see this graph and try to understand. So this is the values that I have found, that atomic radius values. If you need, you can take a note of this. Now the values which are given without bracket, so that tells the single bond covalent radius. Single bonded covalent radius. And within the bracket, so these values which are inside the bracket, so that gives atomic or metallic radius. So in the atomic state, so these values are in the atomic state, whereas these values which are non-bond without any parenthesis, without any bracket, so that gives a covalent radius. And yeah, these values are given in picometer. So picometer is actually 10 to the power minus 12 meter. So 1 picometer is 10 to the power minus 12 meter. So our hair is in the order of micrometer, 10 to the power minus 6 meter. Now, if you divide this 10 to the power 6 times, that will be a picometer. Then you can understand how much tiny that value is, how much smaller the value of an atom or radius of an atom is. Now we will discuss about some concepts regarding atomic radius and ionic radius. So cations having lesser number of electrons experiences higher electrostatic attraction, giving lesser radius compared to its elemental form. So let's see, we have these elements here in the elemental form: lithium, sodium, potassium, beryllium, magnesium, calcium, and in this side we have fluorine, chlorine, bromine, iodine. Now these atoms, here we have similar number of protons and same number of electrons. So number of proton and electrons are same. But when we take out an electron, in that case number of proton is more and number of electron is less. That time we get cations. These are the cations. And when we put an extra electron in this elemental form, so that time we have lesser number of protons and we have more number of electrons. So that time we get anions. So these right hand side ones are the anions. Now it is saying that cations having lesser number of electrons because we have already removed one or more electron, right? So in this case we have removed one electrons from lithium, sodium and potassium. So it has now less number of electron, one less electron. In sodium we had 11 protons and 11 neutrons, sorry, 11 protons and 11 electrons. Now we have removed one, so now we have 11 protons and 10 electrons. So we have less number of electrons, and that experiences higher electrostatic attraction because now we are removing one electron. So one lover is removed. So now the nucleus or the attractive girl, that can give more love to each electrons, right? So that can give more time or more attraction. So that's why the electrons feel more attraction now. Just I will try to clear this concept here. See, this is my nucleus and these are the shells. Let's see in case of sodium. In case of sodium, we have 2 electrons here in the first shell. Then we have 8 electrons in the next shell. And we have 1 electron in the last shell. So this one is in the last shell, right? Now what happens when we remove this electron? If we just remove this electron, we take it out. So sodium becomes sodium plus. And in that case, this orbit is completely empty. This third orbit, it had only 1 electron. Right now it is 0. So you can see only these 2 orbits are there now in Na plus, sodium plus. So obviously the number of orbit is less. And even if you take magnesium, so in magnesium there were 2 electrons. And if you remove 1 electron, that time we will have a total 12 proton, 12 number of proton and 11 electrons in case of magnesium plus. But when we do magnesium 2 plus, that time we are removing both the electrons. This is also we are removing. So whenever we are removing both the electrons in case of magnesium, again this third shell is becoming vacant, 0. So that time we have 12 protons and 10 electrons. So we can see the number of proton is more, number of electron is less. So the attraction towards the nucleus for each electron will increase, and that decreases the size. So that's why cations are always in smaller size compared to their elements. You can see in case of lithium, the size is more compared to lithium plus. The sodium size is more compared to the sodium plus. Potassium size is more compared to potassium plus. And these are in given 10 to the minus 10 meter. Okay. So if you want to convert it into picometer, just multiply by 100. So this is 203 picometer, and this is now 138 picometer. Similarly, in case of beryllium, we had 96 picometer size, but beryllium 2 plus is only 45 picometer. Magnesium 1.45 picometer and Mg2 plus is only 0.72 picometer. But in case of anions, let's see the case of anions. Anions having higher number of electrons experiences higher electrostatic repulsion. See, in case of anions, in case of fluorine, If you take fluorine, so we had this, I will draw here. This is the nucleus, this is the first shell, and this is the second shell. So in the first cell we had 2 electrons, and in the second cell we had 7 electrons in case of fluorine. But when we are putting 1 electron, so we are putting one more electron here to here in the orbit. So we are doing 7 plus 1. So 1 electron is increasing. Now we have 2 electrons in the first orbit and 8 electrons in the next orbit. So in case of fluorine minus, we have total 9 protons but 10 electrons. So we are putting one extra electron. That electron, so we already had several electrons. We already had 7 electrons, and then we are putting one more electron. So what will happen if we increase more number of students? There will be more chaos, right? More fight, more quarrel. So when we are adding one more electron, that time the electron-electron repulsion increases. And because of that electron-electron repulsion, these electrons will try to go away from each other. This will try to go this side, this will try to go this side. So that will actually expand this orbit size. So because of this, the size of fluorine is smaller, but the size of fluoride ion is actually much bigger because these electrons are trying to go away from each other. So as we are putting extra electron, the electron-electron repulsion is increasing. Those electrons are trying to go away from each other, and because of that, the shell is expanding, and we are getting higher value of radius, ionic radius or anionic radius, compared to the elemental form. You can see even in case of bromine, in the elemental form it was 120 picometer, but in the bromide form it is 196 picometer. And you can see the expand of iodine as well, from 139 picometer to 220 picometer. So we have understood that in case of cations, because we are removing electrons, so either the shell number of shell is decreasing or the electrostatic interaction is increasing. So both factors are reducing the size of the cations. It may happen that the shell is decreasing, means earlier it was 3 shells. Now in case of sodium plus, there are only 2 shells. Similarly, in case of magnesium, it had 3 shells, but in case of Mg2 plus, there are only 2 shells. Or even the shell number is same, but still, if you remove electron, that will increase the electrostatic interaction. So because of that, the size of the cation is always smaller than the elemental form. And as we are putting extra electron, so that will increase the electron-electron repulsion. So because of that, the orbital or orbit will try to expand. And for that reason, the size of anions are every time bigger than the elemental size or elemental radius, right? Next point is similar charge species along a group follows the same periodic trend as of the corresponding atoms. So the ionic radius trend follows exactly the same as the atomic radius trend. For example, we see in case of lithium, sodium, and potassium, if we go from top to bottom, we can see the size is increasing, the atomic radius is increasing. Similarly, if we consider lithium plus, sodium plus, and potassium plus, we can see here also the size is gradually increasing from lithium to potassium. And that is the thing, this ionic species, if it has same number of charge, that will every time follow the same periodic trend as of the elemental forms. So even if you take electron or give electron, if you convert in the ions, and if you convert in the same nature of ion, if it is 1 plus, you have to compare it with 1 plus charge. If it is 2 plus, you have to compare this with the 2 plus charge. So if you do so, you will have the same periodic trend as of the atomic radius trend. But yes, you cannot compare the lithium plus to fluorine minus, F minus, right? These are not same charges. You can see here it is plus 1, here it is plus 1, and here it is minus 1. So you cannot compare those to take the periodic trend, or you cannot compare this plus 1 to plus 2. So these are not similar charge. If you have similar charge species, only then this rule will apply, and the ionic radius trend will exactly follow the atomic radius trend. Right? So what we have learned in this segment. So from this segment, we have seen that the trend of atomic radius is actually a DL property, down left property. So it increases in the down and left side. And the size or radius of an atom decreases from the left to right of a period. We have also learned that size or radius of an atom increases from top to down of a group. So what we have observed, that from here to here, from left to right, it decreases, right? So we can see from right to left, it actually increases. And we have also seen that from top to bottom, it increases. So from top to bottom, it is increasing, and from right to left, it is increasing. So that's why we can see that this is the arrow which tells in which side the atomic radius is increasing. So that's why if you go back to my first slide, you can see that I have given a small arrow on the side, on the right hand side of periodic trend of atomic radius. Next point is that alkali metal ions are having highest atomic or ionic radius and inert gases are having lowest atomic radius in a same period. The variation in ionic radius for a particular oxidation state follows the same trend as of the atomic trend. And additional information is that radial distribution function of the electrons in the outermost shell is required to calculate the atomic radius. So we calculate this atomic radius from the RDF function. So it is theoretically calculated in a free atomic state as the distance from the nucleus to the point at which the radial distribution probability of the outermost orbital electrons is maximum. So theoretically we calculate in a free atomic state this atomic radius, which is from the center of the nucleus to the outermost electron orbital, or where this radial distribution probability function is maximum.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.